right, let's get into LAN Basics. Okay. All right, and this is getting to the end of our, our network fundamentals. Okay. At this point, you've learned a lot of stuff as far as the network basics, OSI model, TCP, UDP, secret numbers, Ethernet. Okay. So we've gotten a lot of stuff covered already. So let's talk about our network types. Okay. All right. Once again, our acronyms. Okay. A PAN. This will be a personal area network. Okay. All right. We talk about area as means of a domain. Okay. So on a and personal would be something that is kind of like just for yourself. Okay. You can actually think of a Wi-Fi as a personal network, especially if you're the only one that's actually using it. Okay. All right. But it's really meant for things like a remote control. Okay. All right. That's a personal network. And you got to understand, anytime you are communicating with a device, with another device, you are networking. Okay. Or a remote control is a network. All right. It uses frequencies. Okay. But you're still communicating. You're communicating to turn the power on in your TV, to change the channel. All right. You don't have to physically get up. You are literally communicating with that television via a remote control. Okay. Also, a personal area network would be Bluetooth. Okay. That really is personal. Okay. All right. Now, your land, okay, your land is local area network. Okay. We call it local because, as you can see here, we got a router. All right. And from that router, we actually have a switch. Now, remember, your router, remember, you can't have more than one interface on a network. Okay. The only way to actually get two interfaces on the same domain is to bridge them together, what you can do. Okay. However, all right, one of your interfaces has to be on the network that your LAN is in. Okay. Inside the LAN, okay, you can have a switch, okay, to connect multiple devices. Okay. Within that LAN, and I've seen it, you can literally have firewalls, okay, separating your actual LAN devices, sitting in between switches, in between hosts. Okay. All right. Anything is possible. All right. As long as that local area network is yours, meaning that anything that's sitting behind the router going into your space, into your building, okay, is local. Okay. All right. Anything on the outside, which is going to an ISP or to a WAN connection, okay, all right, and that WAN connection stands for wide area network, meaning that it's wide. It's not local in your building. Okay, it's outside your building most of the time. All right, which will be the case. Okay, because even if I have going from building to building, okay, if that building is a couple of streets down, okay, all right, you have a wide area network between the buildings. Okay, and then you have a LAN inside each building. Okay, does that make sense? All right, then you have a MAN, okay, which is metro or metropolitan area network, okay, where you're connecting cities together. Okay, all right, and then you have, the cloud, what you talked about. We don't know what the hell's in the cloud. That's why we use the cloud as a means of saying, I don't know what the fuck's in there. I can't, but technically I don't know, and I really don't care. As long as whatever's in the cloud handled by somebody else, as long as it gets their traffic from end to end to get to my other site or my other location, my other destination, that's all I care about. Now, normally from getting from end to end, you would pay for a service to get that done. Frame relay, MPLS, ATM. Okay. Now, from that perspective, okay, do not think frame relay is not still out there. Okay. All right. Let's look at a bank, for instance. Why spend MPLS services for every branch of a bank? Okay, like someone like Bank of America. Why would they pay that when they could just do a frame relay circuit? Okay, all right. And the bottom line is they don't need that type of speed because really what they're only transmitting really is ATM information, and maybe someone needs to just when they create an account to update that information to a server located at the corporate office. All right, so a high speed connection isn't really that necessary, and not to mention the fact. Don't get me wrong, all right? Because Verizon is still bringing. Because I was shocked to realize that my mom has a gig of speed going to her house. I'm like, what the hell? Who the hell needs a gigabyte? When me spending extra money to get 400 megabytes per second, okay? I had to bring that back down to 100 megabits per second because I sat there and scratched my head for a little bit, and because I couldn't get over 100 megabits per second, and I kept calling them. Right now, of course, it didn't last past a day. But again, I'm like, wait a minute, hold on, wait a minute. I'm on 10 megabits per second, okay, or 100 megabits per second. No wonder I can't get over 100 bits, okay, on my devices when my switches don't even do gigabyte speeds. Okay, so there's no way I can utilize 400 megabits per second. So I had to go back down to 100, all right? And I would get about 98, 99, okay, but never get 100 because remember, your speeds on your switch ports are up to, okay? Now, where a hub is sharing your bandwidth, a switch is literally isolating that bandwidth in two bi-directional ways, okay, to literally give you technically, especially if you're doing full duplex. Now remember, half duplex, only one person on the wire can speak at a time, okay, and whoever's speaking, okay, gets the actual bandwidth. Where full duplex, I can talk, I can transmit and receive at the same time, and you're getting 100 megabits per second or gigs or gigabyte per second speed, whatever you have on your switch ports, and you're getting it in bi-directional. So technically, okay, you're getting 100 megabits times 2, okay, or a gigabit per second times 2, meaning you're getting 2 megabits per second of speed or bandwidth as you're transmitting and receiving at the same time. Okay, another beautiful thing of a switch. Okay, all right. Now, how big can a LAN be? As big as you want it. Okay, all right. Now, something that has limitations like an OSPF routing protocol. Okay, all right. After a certain amount of devices, you're going to start having problems as far as the database getting propagated and things of that nature. So segmenting those actual large devices will be wise. Okay, if you put 10,000 devices on a LAN, imagine what happens, okay, when all that traffic, okay, from all those PCs, okay, you see how chatty a PC is with Wireshark. Imagine all that happening with 10,000 PCs on the same LAN, on the same network. Okay, your bandwidth is going to eaten up and it's going to be extremely slow because it's too many devices on your LAN. Okay, so using subnetting to separate that traffic. Okay, all right, another reason why we would use subnetting. All right, another reason is to bring down the broadcast messages so we're not having broadcast storms. All right, now broadcast storms is watching a broadcast traffic go around and round and round and round, and you can easily do this, okay, literally by turning off spanning tree. Okay, our spanning tree will actually in the background shut down loops in your network. All right, because we love redundancy. All right, you shut that spanning tree off, okay, and allow those loops to exist. You will watch your switch, literally, let's say you have 10 devices, you will watch those switch lights start to increase, and they're blinking, right, telling you that data is being transmitted, and to the point where it is so fast, okay, that, you'll be like, wow, look at that. Okay, so just keep that in mind. Now, um, our LAN devices. All right, switches. Okay. Now, even though a router is a layer 3 device, okay, yeah, see, now it's easy to understand that term now. Even though it's a layer 3 device, okay, one of those interfaces will sit in your LAN. Okay, so it is a LAN device from that perspective. Okay, hubs, bridges. Now remember what a bridge is. A bridge is a concept of bridging networks together, whether it's on a layer 2 perspective, maybe it's on a layer 3 perspective. I'm taking 3 routed interfaces and bridging them together. Now, a bridge is a layer 2 technology. So if I'm bridging the interfaces together, okay, those two interfaces are now transmitting or sharing information between the interfaces via layer 2. Now, the layer 3 concept comes into play by me creating a logical layer 3 interface to move traffic on a layer 3 basis. Okay, so bridges are layer 2 technology. All right, now repeaters. Repeaters is the concept of taking data in, all right, killing that packet, copying that packet, and re-energizing it, I should say, all right, and sending that traffic off. Now, with Ethernet, okay, very important. Ethernet can only go at 100 meters, okay, before it starts having issues as far as strength is concerned. 300 feet. If I have an actual cable of Ethernet that is 300 feet in length, okay, and I'm going over that 300 feet, let's say it's 400 feet, you're going to have transmission issues. You're going to have drop packets. You're going to have corrupt data. You're going to have errors on your interfaces, okay? Now, the only way to fix that is at that 300 foot mark or before you hit 300, all right, you put a repeater on there, all right, or you add a switch, okay, because that's what a switch is going to do, is going to regenerate that packet and send it on. So every 300 feet, I have to have a switch, okay, or I could buy a repeater. I've never purchased a repeater. Matter of fact, uh, I've never actually even seen one. Let's actually see what it looks like. Oh, okay. All right. Okay, so that really is just a single, I have seen these. Okay, I've seen these and I've also seen them as taps as well. Okay, all right, I've seen repeaters and taps. Matter of fact, that exact similar device is one of the contracts I worked on. They had all types of taps in there, man. It was complicated as hell, but it was awesome as God knows what. Okay, all right, so let's go back here and let's see. Where does the land end? Okay, we already know what the purpose of a land is. The land, the boundary of a land, is always going to be where your devices plug into the switch, okay, and it's not going any farther. Okay, now I want you to think about this. If I have a PC plugged into a switch port, the PC is the boundary of that land. Okay, that particular PC on that side of that switch port. Now, if I connect another PC, okay, to that PC with a crossover cable, okay, and allow traffic to go through that actual device, okay. Now, Windows won't do that normally from what I know of. I've never tried it with Windows 7, Windows 10, or whatever. I don't know if it'll route traffic if you have two network cards, because Windows isn't really set up as a router. Now, you can actually set up a Linux device, okay, like a VM, all right, and use Linux as a means of as a router. You could definitely do that, but you will have to have some type of software that will actually do that, and I don't know why anyone would do that. Okay, might as well just get a router. But nonetheless, your LAN would now extend past that PC plugged into the other PC. okay, your LAN also will, is the moment you put a router and a firewall where you are going to another network, okay? Because firewalls can do routing too. You can use them in transparent mode too, as far as pretty much a bridge, all right, letting the traffic go through and blocking that traffic as it transparently goes through the firewall, meaning there is no hop from a TCP/IP perspective. It doesn't even know the firewall is there. All right. So now that's why we call it transparent mode. Now, from that perspective, your boundary, okay, and I need you to understand, if you are using a firewall in a transparent mode and allowing that traffic to move through, okay, your boundary is going to expand past that firewall. All right, because you are using in transparent mode. You're just sitting there. It's like an invisible device just sitting there monitoring traffic and blocking traffic that comes through or allowing it to go through. All right. As a router, though, that is a layer 3 device, and that is where your boundary stops. Okay. And as you go over to another interface, a new boundary begins, okay, as you're routing traffic from one network to another. All right. Okay. IEEE. Now remember, 802.13 is our, or 802.3, sorry, 802.3 is our Ethernet standard. IEEE, okay. Let's go to IEEE. All right. Let's go. I think we've done this before. Do 802.3. Ethernet, local area network operation, is specified for selected speeds of operation from 1 megabits per second to 400 gigabits per second using a common media control. Okay, now you know what MAC address stands for, right? Specifications and management information base, which is an MIB, right? Management information base. The carry sense multiple access collision detection, which we will talk about. I believe that's actually on our list here. Yes, okay, that's coming up soon. All right. Protocol specifies shared media half duplex operations and as well as full duplex operations. Speed specific media independent interfaces allow use of specific physical layer devices. See all these acronyms? It never stops. For operation over coaxial twisted pair of fiber networks or electrical backplanes. Okay. System considerations of multi-segment shared access networks describe the use of repeaters that are defined for the operation speeds of 1,000 megabits per second. I mean, that's all your switch is. As soon as you plug it in, that's all it is, a repeater. All right. Local area network operations is supported at all speeds. Other specified capabilities include various physical, what was that word? Physical layer devices. Okay. All right. Whenever I read, okay, I always say the exact what the acronym is. That's the only way that I actually get it put into my brain what that acronym is. Every time I read documentation, all right, I'll say it out loud, and I'll go back to find out what the acronym is again. So just saying PHY, because I'm never going to remember what the hell that is. All right, types for access networks. Physical layer devices suitable for metropolitan area network applications and the provision of power over selected twisted pair physical layer devices. Types. Okay, now, if we go down here, okay, I read that for a reason, by the way. All right, I'm not going to read this one. All right. Come on, get me to where I need to go. All right, here we go. Taking this sweet time. There it goes. Oh my God. Are you serious? Okay. Will you get me somewhere to get me to the actual page? It just keeps on going. Okay. All right. You know what? I just want you to see the format of how it's actually read. There's a name that it's called, and I can't remember at the top of my head right now because I'm having a brain cramp. All right. Um, God, what is the name of that actual document? I really want to show you that because that really is the most important aspect of you being an engineer because a lot of your engineering is documentation, going through reading. And I don't know why this is so hard to get through. Now, hold on. Hold on. Oh my God. You guys made this thing horrible. And I'm not kidding. I mean, horrible. I have to go through and find out and just make a video I guess, just on that. Because this is ridiculous. I mean, all you're doing is telling me what the documentation is. Where the hell's the documentation? Wow. Let's take a look at this one. None of this has the actual information, the standards of that actual protocol. Okay, the way it's written. All right, it pretty much looks like it's written in a notepad. Okay, and none of this is showing me. I don't know why the hell this is so difficult to find and why IEEE did that. But nonetheless, we'll cover that in another video. All right, and let's go back to my OneNote. Okay, now the data link layer. Okay, this is something we haven't talked about yet, and that's what we're going to do right now. All right. The data link provides reliable communication over a media. Okay, this is done at layer 2. All right, it uses something that's called LLC or logical link control layer. All right, this is the concept of doing frame synchronization, flow control, okay, and errors. All right, now if I actually go into my device here, you know what's funny? I don't think you can see when I go off this OneNote screen because of the camera. I'm gonna have to go back to the video and check that. What is my timestamp here? 23:29 or 23:20 or 30. Okay, I'm gonna actually go back and take a look at that. All right, because I'm gonna bring up this actual page here, and okay, I hope you can see this. But at this point, okay, you can see here on our interface, and what I'm doing is I'm logged into a switch and I'm just taking a look at one of the interfaces. Okay, all right, and where the hell are you at? There you are. Okay, two input errors already. All right, don't know where they came from. All right, but still at the same time I have two input errors, and this is part of the logical link control, the LLC. All right, it acts as an interface between the media access control and the network layer. It provides multiplexing mechanisms, right? Okay, which is nice, so we can actually send multiple pieces of data on the actual wire. Okay, and it determines when a device can send. Now we get to CSNP. This is part of Ethernet's protocol. Okay, carry, sense, multiple access detection. Now, back in the day when we were running coax cable on a bus network, okay, so we have several types of topologies, okay, bus, which is a straight line, a ring, okay, topology is something that's sitting on a circle like a fiber ring, okay, and a star topology is where everything is hooked up to one source, okay, and the source sits in the middle. All right. It doesn't mean that this is how it's physically connected from that concept. This could be a logical diagram that you create to show all the connections going to the one device. All right. That's why we call it a star. Now, if we go back, I'm afraid that you can't even see even when I go to the internet. And if that's the case, I'm going to have to start capturing the whole screen. All right. So now, okay, carry sense multi-axis collision detection. Only it listens onto the wire at all times, okay, and only when the wire is free, it will transmit, okay. Now, that's the carry sense multiple access part. The collision detection is if two PCs hear silence, okay, and believe that they can transmit and send out messages, okay, at the same time. What happens is that data collides and it kills each other's data. At that point, voltage on the wire will change, okay, as it's monitoring that voltage, okay. It'll know a collision is detected. Now, back in the day when we had active hubs, now you got passive hubs and active hubs. Passive, no power, okay. There's no way to determine what's happening or what's going on except the fact that, your communication is going to be slow. But with power, okay, an active hub, all right, you actually had a actual light on your hub to show you every time a collision happened. And if that light was flashing like crazy, you knew you had something like a broadcast storm or something like that, okay, and all you do was unplug the hub, okay, all right, or shut down your interfaces or disconnect your cable, all right, and plug it back in. That way that carrier sense can actually go back to doing what it needs to do, all right, and reset it. Pretty much what you're doing. You're actually just unplugging the interface and plugging it back in, right? Okay, and then everything will start working again, okay? All right, but you could actually see every time there was a collision, all right? And then actually had an actual label on the actual light that said collisions. Okay, now when that actual collision happens, Ethernet will actually send out a random clock time interval for each PC, okay, meaning that randomly, that means no one's going to get the same amount of time to transmit it, all right, but they will cease communication for that period of time, and then they will start communicating again to eliminate the collision. Okay, making sure that they do not communicate at the same time anymore. Okay, and it might happen again. All right, and then CSMACD will kick in again. Okay, all right. This was great, a great protocol. Okay, to eliminate broadcast domains. Broadcast storms. Okay, and if you're wondering what a broadcast storm is, obviously it's a broadcast that gets sent out, keeps going around and around and around and around, and it starts copying itself, okay? Because as I'm sending it to 5 PCs on that broadcast domain, they're going to respond to that broadcast, all right? So now I got 5 more PCs going out, okay? Then it's going to go back to that one PC. That PC is going to communicate with that, okay? And now you got this data going around and around. At no time does it actually dies on a layer 2 transform or transport. Okay, now layer 3 has a time to live. Okay, so after so many hops, that packet just dies. The router will kill it. All right, but layer 2 does not have any type of time to live. So we have to worry about that broadcast storms. All right, and that's why we call it a storm, because it gets out of control. Right? It's just packet after packet after packet, or frame after frame after frame. All right. Now, most important aspect: collision domains and broadcast domains. Okay, remember what I was talking about? Where does your LAN go? Each one of these PCs is the end of our domain. Okay, where this router is sitting, that interface that the router is connecting to my switch or connected to my LAN, it is part of the broadcast domain. All right. Okay, it's the only way to actually get traffic to the router. It has to be part of my broadcast domain. All right. As engineers, we'll talk about broadcast domains a lot. Okay, from a perspective of, well, if well, sir, that depends if that data is on the same broadcast domain. Okay. All right. That person might not know what I'm talking about, but other engineers do. Okay. All right. So our broadcast domain is how far our domain goes, or the allowance of our TCP IP network. Okay, that's why we have a network number and a broadcast number, the two IP addresses that we're not allowed to assign to an interface. All right, that is part of our broadcast domain as well. We can have 200 PCs sitting on a physical domain. Okay, however, if our TCP only goes up to 63 addresses or 64 IP addresses because we subnet it, our broadcast domain is not going to be a physical topology, but more of a logical boundary. Okay, that will be set by TCP/IP. Okay, because it's not going to be able to communicate on the other network. All right, so keep that in mind. Now, our collision domain, remember I talked about the hubs and the collisions. Okay, all right, everybody who actually is sitting on that hub is part of that collision domain. Okay, all right, another good thing about a switch is every single port, okay, it's its own separate collision domain. Okay, that's great. That's fantastic. All right, that eliminates our means of actually having multiple devices being able to collide with each other as far as they're communicating, because the switch will actually isolate that collision domain via each port that devices are connected to. Okay, so do you see the difference? And it gets confusing because if I'm asking you a question on the exam, all right, I'm going to say how uh, uh, how many PCs are within this collision domain, all right, and I don't have a switch connected to it, I have a hub. All right, the answer would be 3 devices. Okay, 3 devices are able to collide with each other. All right, so you need to understand the difference between a broadcast domain and a collision domain. Okay, MAC addresses. All right, last section of our LAN fundamentals, our network fundamentals. Okay, and if you've gotten this far, great job, guys. MAC addresses are hexadecimal. Remember, we were doing our binary. Okay, remember, every number, okay, is 4 bits in length. And if that's the case, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, times 4 is 48 bits in length. It's a 48-bit address, and each one of those numbers, okay, allows 4 bits. Okay, so 4 bits, 1, 2, 4, and 8. Okay, 8 plus 4 is 12, plus 2 is 14, plus 1 is 15. All right, 0 through 9, okay, and then to get us to 15, we have A, B, C, D, and E, and F, okay, to allow us to represent a 11, 12, 13, 14, 15. All right, MAC addresses are known as layer 2 addresses. They are physically burned onto the actual network card of your NIC. Now, I can logically change that MAC address to whatever I want if the software allows it. Okay, I don't know if Windows allows it or not, but still, okay, with a MAC address, okay, I'm sorry, with a router, yeah, I could do this. I don't know if I could do it on a switch port. I believe I could do it on a logical interface. Actually, I don't even know if I could do that. That's something we could test later on. All right, so now, okay, these are physical addresses. Now, people believe that these numbers are unique, and never in history of man will there ever be a network card that has the same MAC address. That's just not true. The chances of you seeing it is slim to none, okay? But I have experienced it. I have seen it. I have set it side by side and read the actual MAC addresses off the network cards to different manufacturers, okay? All right? And actually, I don't know if it was two different manufacturers or the same manufacturer. But somehow, okay, those MAC addresses were identical, all right? And it caused issues when trying to communicate on the network, all right? Long story short, I had to get rid of that network card and buy me another one so I could have a separate MAC address because I couldn't change it in the operating system. I think it's back way back in 1990, Windows 95, all right? So don't think that it can't happen. All right, so be aware that you must have unique numbers on your network. Okay, do your due diligence. Check the MAC addresses. Make sure they're not the same. Okay, like I said, slim to none. All right, okay, the chances, I've only seen it once, and I guess I got lucky. All right, now you also got to understand the more you tinker with stuff, the more you involve yourself with things, the more times you will see things that other people won't see. Okay, so if you're an IT guy within your heart, this is a given. You're going to tinker. You're going to do things. You're going to say, I wonder if I can do that. Okay, and it's going to make you a better person as far as knowledge is concerned. Okay, now these MAC addresses are called physical addresses, burnt-in addresses, okay, hardware addresses. Every network card you buy from like Best Buy, you should be able to see the MAC address with a sticker on the back of the card telling you what the MAC address is. All right? Or you can go into ipconfig, whatever, okay, whatever floats your boat, okay? Now, remember, the first 6 digits are what we call the OUI number. Now, this number, okay, is what's given to a manufacturer, and every network card that manufacturer makes will have the exact same first 6 numbers. Okay? All right? Now, how did I get 2 MAC addresses if they were different manufacturers of the same IP address? I mean, of the same MAC address, because apparently that one manufacturer wasn't going through the organization to actually get their numbers assigned. They were just assigning MAC addresses to their net cards, because when you actually went back and took a look, you'll notice that the first 6 numbers were never the same. They just randomly created MAC addresses on the net cards. Okay, they're doing something they're not supposed to do. They're not following standards, and that's why one of the network cards got trashed, and I never bought from that company again. All right. So that's the whole purpose of why we have standards. There's so many things working in the background. Okay, things have to be precise in order for things to work. So you follow a standard. Okay, all right. Now the last 6 digits are, think of them as host. Okay, think about, now you don't have to be on the exact same first 6 digits, okay, in order for you to be like on the same network, like an IP address. The reality is, as long as they are unique and different, they can communicate all different manufacturers all on the same LAN from a layer 2 perspective. Okay, now if I send out and set all those bits to an F, all right, meaning that my 2, my 3, my 4, my A, and my 4, all these numbers are set to F. That switch is going to send that data out all ports except the one it came in on, just like an unknown MAC address. And in fact, you know, when I'm going out with an ARP request, that's what I'm doing. I'm setting my bits all to F to symbolize a broadcast, because I have no idea what's the MAC address for that IP address. All right, I'm trying to build my table, so I have to send it to everybody, hoping that someone responds on that actual segment. Okay? All right? And that concludes our our LAN basics and our network fundamentals. We have gone through, this is starting from scratch. We have covered things that you need to know moving forward. Okay? All right? This is literally network fundamentals in a nutshell. All right? So we covered a lot of information. So I'll see you guys on the next one. And always remember, you know what I'm going to say, be strong, be determined, be Cisco.